All right, so I only printed 5 copies. But hold on a second. Hold on a second. All right, guys. This one. Hello? Who? No, no, it's not me. No, no. Yeah, good. All right. All right, guys, good afternoon. All right, so I'm recording the session so that you can have an opportunity to go back through what we are doing today. So the topic for today is surds, logs, and indices. Now, we actually started this topic in the last class. All right? So it's not going to be that I'm going to teach it all over again from scratch, right? But I can share a video of the content that we did in the last class on this topic, which will still give you some coverage of what we did. So today we're really continuing, with those topics, surds, logs, and indices. So it's a matter of practicing some questions, and then I'll give you a classwork to do. And you all know the classwork already. You have to get everything right before you can leave. When you did C-Sec, you would get 1 or 2 questions for your classwork. This is pure maths and odd maths. So you're getting like 8 questions. All right? Not lengthy questions. All right? You have to get them right. Sometimes on a Friday, I can tell you from now, Friday's an action day, a work day. Sometimes on Friday, the classwork is so lengthy. People leave here at 10 o'clock, 10:30. Understand? You have to get everything right before you can leave. If you're good enough, then you'll finish at 7 or 8. But you finish with classwork quick and fast. You get me? All right. So I'm just going to do a quick recap of some of the things that we did in the last class, just for the benefit of the persons who come in for the first time. There's a document that I'm going to share with the group. It's called a must know. Let me see if I can find it here. It's called a must know document that I have. All right. Let me see if I can find it over here so I'll show you. So you can have a look at it. So this will be the odd maths one. So this is how it will appear. And the pure maths one is very similar to this one. Everything that you need to know is summarized in this single document. Right? Everything that we need to know. So for example, the remainder theorem, it's summarized right here, as you can see. What you need to know right here. And we have factor theorem, which is something we did already. These topics we did already. It's there. Then we're on this topic now, which is logs. All of this is logs. So right in this section are all the things that you need to know about logs. Right? And apply. Right in this section right here, this little box. Right? Here as well. Here's some additional information that we need to know. And then we have this. This is an application of logs in odd maths. Reduction of an equation to a linear form. Same thing right here. But if I continue, you'll see everything that you need to know, basically. Not everything, maybe 98% of all that you need to know for your odd maths syllabus is right in here. So it's a quick revision, quick and easy revision. So when I send this document, if you take the time to ensure that you know everything in this document, then the exam will be very easy for you. All right, I promise you. Very, very easy. Everything is inside here. And then there's one for pure maths as well. All right, similar to this one. All right, so I can actually use this. Let me see if surds is in there. I can actually use this to sort of go back over what we did quick and fast. Some of the key things that we did. All right. Some of the key things that we did. All right. So I just wanted to show you that document. And when you get it, make sure that you study everything. Make sure you know everything on it. All right. So the first thing we touched on was surds. We say a surd is an expression usually looking like this. It's an irrational number. For example, square root of 2. It's an irrational number, meaning it cannot be expressed as a fraction with a whole number numerator and denominator. So that's an example of a surd. We said if we have, for example, the square root of 4, this is not a surd. This is not a surd because this we know is equal to 2. And 2 is a rational number. A rational number is any number that can be written as a fraction with a numerator and a denominator that are integers. So for example, 2/3, that's a rational number. 4 is a rational number because it can be expressed as 4/1. Usually, rational numbers, when written as decimal, will terminate. So for example, 3/4 as a decimal is 0.75. That's a decimal that terminates. Rational numbers written as a decimal will terminate. Or they will have repeating values. So for example, 2/3 is 0.66666 and on forever. The values are repeating. If you have a decimal, for example, 0.29292929, this is going to be a rational number. So when there's a pattern in the decimal place, right, a repeating value, those are rational numbers. So the surds are irrational numbers, and there are certain things you have to be able to do with them. All right. So some examples of surds, as I said, would be √2, √3, √5, √7. And they are usually left like this. So when you're dealing with surds in questions, you usually leave them as they are rather than write them out as decimals. If you put this in the calculator right now, you're going to get a decimal, a non-ending decimal, where the values are not repeating. All right? They are called surds, and there are certain special things you must be able to do with surds. What did we say are some of the things we need to do with surds? We need to be able to multiply surds. So for example, we should know that, for example, the square root of 2 squared is going to just be 2. The square root of 2 is square root of 2 is the inverse of the square of 2. So if you square it, you're gonna basically eliminate the square root by squaring it. If you multiply a surd by a constant, you can add them. So for example, √2 plus 3√2. You treat this like a variable or like an entity or like a quantity. This would add to 4√2. Simple stuff like that. Then sometimes with some surds, you have to break down surds out of some higher level surds. So for example, if we have the square root of 50, we can simplify that expression by looking for the perfect square in 50 as a multiple. And this will become the square root of 2 times 25. So you're looking for the perfect square that is in 50. In that case, it's 25. And this now would break out into the square root of 2 times the square root of 25. So the square root of 2 times 25 becomes the square root of 2 times the square root of 25. Then the square root of 25 is just 5. So this then will work out to 5 times the square root of 2. This 5 is from this. And then we have the square root of 2 right here. So this could be expressed as that. Sometimes we have to simplify those expressions as well. All right? That's a thing we have to do with surds. What else other things we must do with surds? We must know that when you multiply a surd and its conjugate, you actually eliminate the surd. What's a conjugate? Let me just show you. So if I write the square root of 2 plus 3, the conjugate of that is the square root of 2 minus 3. See, the sign is changed. All right? If I have 2 root 3 plus 7, the conjugate of that is 2 root 3 minus 7. Get the picture? Sign is changed. And there's a special property of these. When these are multiplied together, they are the difference of 2 squares. And the surd is eliminated. All right? So for example, if I have root 2 plus 3 multiplied by the conjugate, root 2 minus 3, then that is the difference of 2 squares, which then means that this will become square root of 2 squared minus this 3 squared. This would then become 4, no, not 4, 2, sorry. Square root of 2 squared is 2 minus 3 squared is 9. So this will work out to a negative number, which is a rational number. So this is a method that we use to rationalize surds, especially when the surd is in the denominator of fractions. All right? So as an example, if we have, this is a quick recap of what we did already in the last class, guys. I can't go any slow, otherwise we're going to spend the whole class and do the whole class over again. So it is being recorded, so you guys who come in for the first time will have to go and watch the recording. We're going to do some questions on these things and show you what we're doing, all right? So it's going to be good, so don't worry yourself. So one of the things you have to do with surds is rationalize them when they appear in the denominator of fractions. Example. Let's say they give us an expression like, let's say, what's simple one, root 2 plus 3 over, let's do the conjugate of it, root 2 minus 3. Keep it simple. Right now, this denominator is an irrational denominator. And what some questions will tell you to do is to make the denominator rational. We call it rationalizing the denominator. The very common thing that is required for you to do in odd maths and pure maths as well. You want the denominator to be a rational number. So how you make the denominator rational is by multiplying the denominator by its conjugate. So I'm going to take this fraction as given. I'm going to multiply the denominator by its conjugate, which is the square root of 2 plus 3. But because I'm multiplying the denominator with this, I have to now multiply the numerator by the same thing, root 2 plus 3. So it's almost like I'm multiplying the fraction with the number 1. Then I proceed to calculate the denominator by itself and calculate the numerator by itself. I just set up this easy one. The numerator, as you can see, becomes a perfect square. So then this now would then become, so this expression, when I do this multiplication, it would then become the square root of 2 plus 3 all squared divided by, and then this times this is the difference of 2 squares. It becomes the first value squared, which is the root 2 squared, minus the second value squared, which is 3 squared. That's what we get. So this expression is now that. All right? And then if we simplify this, okay, I work out the numerator becomes a perfect square. How do we expand a perfect square? It is the first term squared, which is root 2 squared, plus twice the product of the 2. We have to multiply these two things and double it. That's how you expand a perfect square. But go to that. But I know to expand a perfect square, right? First term squared, twice the product of the 2. Remember, all I do is C second. So I'm assuming that you have this knowledge, right? If you don't, then you need to top up. So the first term squared is that, then twice the product of the 2, meaning you multiply these two things first, When you multiply them, you're going to get 3 root 2. If I multiply this times this, it's going to first become 3 times root 2. But I have to double it. So it's twice the product of this. So it's become 2 times this product. So I have to double that. And when I double it, it becomes 6 root 2. Plus the second term squared. The 3 squared now is 9. That's what the numerator becomes that. And then the denominator now, this denominator now becomes this root 2 squared is just 2 minus this 3 squared is 9. So you see there's no surd left in the denominator. The denominator is now a rational number. So you get rid of surds by multiplying them by the conjugate. People doing pure maths. There are topics when you will need to rationalize the numerator. Yes, there are questions when you will need to rationalize the numerator. A topic where we'll be differentiating from first principles. There are certain expressions where you will have to rationalize the surd from the numerator. But we'll get to that visual process. But for now, this will now simplify into the root 2 squared here is just 2 plus this stays 6 root 2. This stays plus 9. And you're dividing this by this is now negative 7. Negative 7 is a rational number. So we have removed the surd. Where do we start? We start with this expression. This expression is now this. We can actually put the 2 and the 9 together to make it 11. So final result is that it is 6 root 2 plus 11 over negative 7. That's what this expression became, this one. What was it before? It was this before. Let me write it in a different color. It was root 2 plus 3 over root 2 minus 3. And this expression is now this. Now, if you have a good calculator, you can actually type this in the calculator and it will give you this result. But the calculator tends to rationalize the denominator of surds expressions. So try it for me. Put it in the calculator and see what you get. Hopefully, one of those good calculators that can do that. And that's one of the main things that you have to do with surds, rationalizing them and so on. So you have to simplify some of them, as I did with the root field, and you'll have to rationalize some of them. Right? And you have other operations you have to do with them sometimes. Got it? Got it? Got the 7 under here? Good. But the calculator will rationalize it for you. But the calculator tends to want to give a result with the denominator as rational. You got it as well? You get it? Calculator give you that, right? So that's an operation that you all need to know how to do. Add maths and pure maths. Add maths will actually get a question that says rationalize the denominator. Give you a question, rationalize the denominator of this expression. Pure maths students, more than likely you won't get a question telling you to rationalize the denominator. You get a question where you have to apply rationalizing surds where it exists, whether it's on the numerator or denominator. You have to rationalize it where it exists. And basically, that's a nut and shell of surds. Quick revision. That surds in a jiffy. But what I'll do, as I said, I'll send the video of the full class when we did it from scratch, right? And actually did some questions. I'm going to do some surds questions, practice some surds questions today. Question is, do I practice the surds question now before I jump over to the indices and logs? Just do a couple questions. That makes sense, right? Let's do a couple surds questions now. And then just for a short while, maybe 2 or 3 questions. And then we'll jump over now and we'll look at the indices. But in particular, it's logs. So it's logs and indices, but in particular, it's logs we're looking at, right? All right, so we'll just find a couple questions. Well, this one don't have any on this sheet. So let me bring up a document that will have some on it. Hold on. The worksheet. Here's the worksheet. I'll bring it up over here. So this has a number of surds questions on it. So we're just going to do a couple of them. All right. Let's go for the first one. First one right there. Did we do this question? We didn't do this question the other day. We didn't do this, right? We did questions past papers. Where did they stop it the other day? That's all? You're not here? But where did the topic? We don't remember nothing. We did some past paper questions. We did some add maths past papers and some pure maths past paper questions. That's what we did. We didn't do any questions from this worksheet. All right? So look at this question, man. So add maths question. This part of it says, simplify this expression in this form. And basically, we need to say what the value of k is. All right? That's what this is about. And this is not difficult because we can say that we're ending up with a root 7 in there. What it is that we want to factorize a 7 out of that 28 and factorize a 7 out of this 343 as well. All right? So let's go like this now. So we are given root 28 plus root 343. This is the same as, this 28 is the same as 4 times 7. I'm going to write as the square root of 4 times 7. So somebody tell me what 7, that is divided by 7 and tell me what you get. So I can know what it's 7 times what? This times 7 is what? No, this divided by 7 is what? What times 7 gives us this? 49? 49? So it's 49 times 7. That's correct? Good. Then what happens here now is that the root of 4 is 2. So this expression becomes 2 times the square root of 7. But understand that? This one becomes this. But understand that? Plus the square root of the 49 is what? 7, right? So this one becomes 7 root 7. Right? So 2 root 7 plus 7 root 7 add to give us 9 root 7. And therefore, based on this, the k is equal to 9. If we compare those two, k is equal to 9. But to go to that, k is equal to 9. Simple question. All right, so that was a quick third one. Let's find another one. Here's another third question right here. Question says, without using a calculator, find the exact value of this thing. Now, when it says exact, it means that you can leave surd in it. You don't work it out and put a decimal. As I said, exact, keyword here. Exact value. All right? So it wants us to work this out. Multiple ways it can be done. Multiple ways it can be done. All right? So we can decide to expand out this and expand out that and subtract them. All right? We can decide to simplify this, simplify this, simplify this, simplify that. Multiple ways it can be done. Not one way to do it. What I'm going to do, I'm going to expand out this. All right? And expand out this. And then subtract them. That's what I'm going to do this time. All right, so let's do it. Just some operations with surds we're looking at right now. All right, and these are past paper questions. These are actually past paper questions. All right, so it gives us root 75 plus root 12 squared minus root 75 minus root 12 squared. I could recognize this as the difference of 2 squared and get it quickly, you know. All right? I can recognize this as the difference of 2 squares and get it quickly. But I can recognize that the difference of 2 squares. Look, if you treat this inside here so as x and treat this inside this as y, they really have x squared minus y squared, which is equal to x minus y times x plus y. Understand that? So this result really is the sum of all of this and this. If you add them up, going inside here. No, we actually subtract them first, going in here. And then when you add up this x plus y, add up that and that, you put the value in there. That's a quick, short way to do it. I'm going to do it both ways. Let me do it this way, and then do it the other way and show you. But recognize this, but can see this, what I'm heading at. That's a perfect square. If I call everything inside this a x, and call everything inside this a y, then I'm really doing x squared minus y squared, which is actually equal to x minus y times x plus y. So here, I would have to put the difference between these, this minus this. And then in here, I would have to put the sum, which is this plus this. And look what's gonna happen when we do it that way. It's gonna become equal to the difference, this expression minus this expression. The root 75 will subtract the root 75. What is that? And the root 12 minus a negative root 12 gonna give me 2 root 12. Agreed? Root 12, remember now I'm subtracting. I'm doing all of this minus all of this. Minus. To go in its bracket. So it becomes root 75 minus root 25. The root 75 is eliminated. Then root 12 minus a negative root 12 really becomes root 12 plus root 12. So it becomes 2 root 12. So this bracket here becomes 2 root 12. 2 root 12. And then I need to add them now. Add this and this. Add them. If I add those two, the root 1275 and the root 75 give me 2 root 75. And the root 12 and the minus root 12 eliminate each other. So all I end up with in this bracket is 2 root 75. But I can appreciate that. Then I'm going to simplify this now. This 2 times 2 is a 4. This root 12, I'm going to write it as 4 times 3 under the root sign. This root 75, I'm going to write it as 25 times 3. Good? Then this now becomes 4. This root 4 is 2. Let me put it in a bracket. This root 3 comes back. Put that in a bracket. This root 25 is 5. Put that in a bracket. And this root 3 comes back. Root 3. But understand all of that? Step by step. Then everything works out nicely. This is 4 times 2 is 8. 8 times 5 is 40. And then the root 3 times root 3 is 3. So this works out to be 40 times 3, which then is 120. That is the answer. So this is stuff you have to be able to do. Now, what you can do to prove that this is right is type this in the calculator. You do the question without a calculator. Type that in a calculator and see what you get. This thing in purple. Answer is 120. Go on, try it. But these are some of the operations you have to be able to do with surds. Huh? 120. I prove that the 120 is correct. All right. So the question is, do we settle with this method or you want to see it done another way? The other way is, I think, is more lengthy. I think this is the easier way to do it. Or the easiest way to do it. Other ways to expand it out and do far more work. This is the easiest way to do it. I think I should use the block. All right. So we're going to settle like that, right? We're going to settle with that. The other way is to expand out this and expand out that and then subtract them and all of that. Answer is going to come to 120 anyway. All right. That's giving you some examples of some operations you have to do with surds. All right. Let's look at another example. All right. Here's one. Look at this one. Question says, without using a calculator, show that this thing is equal to that. So here you know what they do. They made the denominator rational because like they give you this, okay, and put it over 1, and I want the denominator to become that. So it's like we are now rationalizing, we are now making the denominator irrational. That's what we're doing. And the numerator becomes rational. So you see the similar thing. See? Similar thing as I said. Sometimes you have to rationalize it wherever it is. So if we have 11, remember, you know, generally speaking, if you want to eliminate surd, simple. Multiply by the conjugate. Multiply by the conjugate. The conjugate is when the sign is different between them. That is it. Multiply by the conjugate. If you have a surd by itself, like root 2, and you want to rationalize it, if you multiply by a root 2, so multiply by root 2 over 2, this time this becomes 2 over root 2. So it means that root 2 is the same as 2 over root 2. All right? Stuff like that you have to do. But now we're looking at this one. We want to make this turn into that. You have to rationalize the surd where it exists. That's what this one is about. So they give us root 11. Let's go again. Root 11 plus root 7. All right? And I want to turn it into this. I want to turn it into this. So I'm going to treat this as this thing over 1. I'm going to rationalize this up here by multiplying by the conjugate of this, which is root 11 minus root 7. And divide by the same thing, root 11 minus root 7. All right, and then you carry out that operation. Like you multiply by 1, enough. I multiply by a number over itself, right? So like you multiply by 1. So this then is going to become equal to the numerator. This times this, it becomes the difference of 2 squares. The product of the numerator is the difference of 2 squares. So become the first expression squared, which is this squared, root 11 squared, minus the second expression squared, which is root 7 squared, over, then 1 times this denominator comes back as the same denominator. So this just becomes root 11 minus root 7. Now what happens here now? The root 11 squared is just 11, minus the root 7 squared is just 7, divided by root 11 minus root 7. Then 11 minus 7 is 4. 4 over root 11 minus root 7. That is it. Good? That is it. All right. I don't think I'm going to do any more search questions right now. But this worksheet is there in the handout that I gave you. So you, some of you have to get the handout. How again? Just you. All right? Oh, you have to get the handout. Are you ready the last class, right? All right. Huh? And you got the handout. You got the handout from that class. All right. No, I just want to know that I got it. All right, cool. All right, guys. So these are some other search questions here. Like so one here. It says I must express this in this form. Basically, it's just to rationalize the denominator. So I'm going to do this at last. I'm going to do this as the last one and never move on. To look at, remind ourselves of the last, right? The last, right? All right. I'm just going to do this one. So it is 5 minus root 3 over 2 plus root 3. And I want to convert it to this number. You can view this as this over 1. So the denominator is no rational. All right? I want to express it like that. we have to get this surd from under the denominator. How do you get it out? You multiply it by its conjugate. So we're going to multiply the denominator by the conjugate of this, which is 2 minus root 3. So we multiply the numerator by the same thing, 2 minus root 3. That is all. The denominator knows the difference of 2 squares. Let's do the denominator first. So this becomes equal to, the denominator is the difference of 2 squares. So the denominator becomes 2 squared minus root 3 squared. The numerator now we have to multiply these two expressions. Multiply them the normal way. So we multiply this 5 first by each of these two things. Multiply the 5 by each of those two things first. We multiply the 5 by each of those two things. We get the 5 times the 2 is 10. Then 5 times the minus root 3 becomes minus 5 root 3. Then we have to multiply this minus root 3 by each of these two things next. We have to multiply the minus root 3 by each of those two things next. So the minus root 3 times this 2 becomes minus 2 root 3. Minus 2 root 3. And the minus root 3 times the minus root 3 becomes a plus root 3 squared, which is 3. I'm going to put plus root 3 squared. That's what we get. I'm just showing all the work. I could just write 3 for this, but I'm just showing all the work this time. Then we're going to simplify the values now. This is 10. And this is actually 3. Can I write 13? Huh? 10 and 3. This is 3. This works out to be 3. And this is 10. 10 and 3 is 13. We have minus 5 root 3 and minus 2 root 3 give me minus 7 root 3. All over. This becomes a 4 minus this becomes a 3. Which under here becomes a 1, right? Got to go to that? So the end result is that you're dividing this expression by 1. So it becomes the same expression, 13 minus 7 root 3. And so this now compares with this. I've written it in that form. That is it. That's it for surds. Not doing anymore. Not doing anymore. All right. So we'll do some indices. But the indices that you'll most likely get are the this guy's equation ones, right? Indices, like maybe these. All right, so the laws of indices are the same laws that you would learn from C-set days, right? No different. Same laws that you would learn in C-set. The laws of indices. What are the laws of indices? Let's look at some indices now. It's basically knowing the laws. You have to know the laws from left to right and from right to left and apply them. All right? So for example, first law is when you multiply indices with the same base, numbers with the same base. You add the powers. So it's, for example, a to the m times a to the n becomes a to the m plus n. You have to know this rule going this way and going that way as well, both directions. Use some numbers. So for example, if you have x to the 4th power, let's use a number. If you have 2 to the x times 2 to the y, it becomes 2 to the x plus y. I have to know the other way as well. So if, for example, I have 3 to the x plus 2, for example, 3 to the x plus 2 becomes the same as 3 to the x times 3 squared. So I have to be able to pull up stuff like that. And then the 3 squared is 9. So it becomes 9 times 3 to the x. Good? I'll be able to pull them up like that. Then you have the division one now, which is a to the m divided by a to the n. When you divide indices, you subtract the powers. This becomes a to the m minus n. You have to be able to go both ways. Using numbers, let's say you have 2 to the x divided by 2 to the y, and that would be 2 to the x minus y. But again, you have to know the law of going both ways, right? Left to right and right to left. So as an example might be that you have 3 to the x minus 2 this time. And to pull that up. 3 to the x minus 2 is the same as 3 to the x divided by 3 squared. This minus means that dividing. Right? This becomes a 9 under here. So this will work out to about 1. Let's write it like this: 3 to the x over 9. That's what this will become. You have to be able to pull them up like this sometimes. Pull them up. Right? That's the second law. So you have one way we're talking about there. This is the second law that I just did. This is the first law, multiplication. The third law now is basically called the power law. Number 3. Now when you raise a power to a higher power, you can multiply the powers. Right? So for example, a to the m, raise that to the power n. You can multiply these powers. So it becomes a to the mn. A to the mn. And there are times when it becomes convenient to switch these around. Like for example, I might have 3 to the x, and that is squared. Right? Depending on what I'm doing, I'll have it this way. Let me give you this example. Might have 9 to the x. And I write this, I need to get this 3. I write as 3 squared. 3 squared. Write the 9 as 3 squared. Raise that to the power x. Then I can switch these two around because 2 times x is the same as x times 2. So this might be convenient for me to write it instead as 3 to the x or squared. So this becomes that. I have to be able to do that sort of juggling. All right. They will mention the negative power. The negative power means reciprocal. So for example, if you have 3 to the minus 2, this really means 1 over 3 squared. Minus means reciprocal. If you have 1 over 2 to the minus 5, you can bring this up on the top and put it as 2 to the 5th power, like over 1. Right? Reciprocal. So the minus in indices is a reciprocal. Then we have a case now when the power is a fraction. When the power is a fraction. Like for example, let me use numbers. If you have 5 raised to the power 2 over 3, the number on the denominator is the root. The number on the numerator is the power. This is the root that you're taking 5. This is the power that you're raising 5 to. All right? So this thing right here would be the same as the cube root of 5. That's the root. Is cube root. And you raise the 5 to this power squared. So I can apply the square first, or I can apply the root first. So I can instead write it as 5 cube root of 5 all squared. So you say I can apply the square on the 5 first, then the root, but then I can apply the root first, then square. I can go either way. All right, so remember, when the power is a fraction, on the denominator you have the root, the numerator you have the power. All right, and these are some things that becomes applicable and useful. All right, so, let me just do a couple questions on this sheet as well, just to show. I think I've covered the main things that you need to know. Any number raised to the power 0 is 1, right? Any number raised to the power 0 is 1. But I must know that. Any number raised to the power 0 is 1. All right, let's leave it at that. And let me just do a couple questions here where we apply it, right? So look at this question right here now. This one. We're solving x from this. 2 to the x squared equals 16 to the x minus 1. What it is, you need to bring everything to base 2. All right? I'll make the two sides come to the same base, then the powers will be equal. The two sides come to the same base, then the powers will be equal. Simple as that. So in this case, this thing becomes 2 to the x squared on the right side. This is x squared. Then this 16 is 2 to the 4th power, right? So the right side becomes 2 to the 4th power raised to the power of x minus 1. 16 is 2 to the 4th power. Then I can multiply these two things. And so I will get 2 to the x squared equals 2 to the 4x minus 4. I'll multiply this out. So since the two sides have the same base, means that the powers are equal. Powers are equal. Common sense, that's common sense. So therefore, the x squared is equal to 4x minus 4. So you know, solving this equation. That's what you're solving, that equation. So I can transpose everything. The quadratic equation becomes x squared minus 4x plus 4 equals 0. This factorizes in a perfect square. X and 2 and 2 minus and minus. So this becomes x equals 2 repeated. Quick, easy example. Let's bring the two sides to the same base. Right? But I have to split up this 16 and write as 2 to the 4th power. Easy example, that one. Let's look at this one down here. Similar kind of stuff, this one. When I bring both sides to base 3, right? Because 81 has a base of 3, can bring that in base 3. 27 also can bring in base 3. All right? So that is it. These are past paper questions. All right, so we have 81. This becomes, let's write it out. The 81 is 3 to what power? 3 to the 4th power, right? 81 is 3 to the 4th power. 81 is 9 squared. And each of the 9 is 3 squared. So it's 3 to the 4th power. So this can be written as 3 to the 4th power raised to the x plus 1 equals, and the 27 is 3 cubed. 3 cubed raised to the power x. So you bring this side to base 3, bring this side to base 3. Multiply these powers now. I get 3 to the 4x plus 4 equals 3 to the 3 times x is 3x. Both sides have the same base, so the powers are equal. So we can say, therefore, 4x plus 4 at power is equal to this power of 3x. If we transpose the 3x, we're going to get x. Transpose the -4, we're going to get -4. So x equals -4 in this question. Simple as that. All right. I really want us to just jump to the logs. But logs is the meat of the matter, or the main meat of the matter. All right. I want us to do one of those disguised equations. All right. We can maybe do this one. This is another power question. I'll do this one last, and I'm going to look at this guy's quadratic equation. There's some indices in it. So guys, remember now, this is just me revising what we did in the last class. It's a revision of what we did in the last class. Persons who coming for the first time, you have to watch a video of the previous class. Right? To the background. This is me just revising what we did in the last class before I give the class work today. All right, so we're doing this now. I'm bringing both sides to base 2. So I'm going to write this now as 2 to the 3 minus 5x equals. Now this is the same as, all right, this 64 under here is the same as 2 to the power 6. Check it for me. 2 to the power 6. It's the same as 1 over 2 to the power 6 raised to the x minus 1, right? Good. All right. 2 to the power 6. Then this now I can write as 2 to the minus 6. I write this side as 2 to the minus 6 raised to the x minus 1. 2 to the 3 minus 5. But understand that? I want both sides to become base 2. I want both sides to become the same base. When the two sides equal with the same base, then the power is equal. But understand this? I want to go from this to this. Huh? Reciprocally introduce the negative. Remember that, right? Then now I can multiply these powers. Multiply them out. So 2 to the 3 minus 5x comes equal to 2 to the multiply this times this. I'm going to get minus 6x plus 6. It means then that this power is equal to this power. Right? So I can write those. It means then that 3 minus 5x is equal to minus 6x plus 6. So this minus 6x comes over here from a positive 6x. 6x minus this 5x is x. So I end up having an x over here equals. This 3 goes over there and subtract from this 6. You leave me with a 3. That is the answer. X equals 3. All right. I'm going to give you this guy's equation now in surds, in indices. And this guy's quadratic equation. All right, let's look at this one. Make it nice. Let's look at this one. They give you this equation to solve. That's actually a quadratic equation, you know. Actually, this quadratic equation, this guy. Let's look at it. Now, tell if I'm now. When you're solving questions, try not to work with negative powers. I don't want this negative power. All right? So this thing is going to become x to the 1/3 minus, and this now is going to become minus 4 over x to the 1/3, and that's all equal to 3. But I can see that. I can see that. This x to the minus 1/3 becomes this 1 over x to the 1/3. All right, that's what the negative does. Remember, the negative on the power means reciprocal. Then what I'm going to do, I'm going to multiply through by this denominator. I'm trying to solve it, expand it out into separate terms. I'm going to multiply through by that denominator. Let me write it in red. Multiply by x to the 1/3. Multiply all around by x to the 1/3. So this will become x to the 1/3 squared. X to the 1/3 squared. This becomes minus 4 equals, this becomes 3 times x to the 1/3. What good at that? That's a quadratic now, you know. This is a squared term, and this is like a x. This is like a x squared, and this is like a x. I'm going to transpose this over this side. I'm going to get x to the 1/3 squared minus 3 times x to the 1/3 minus 4 equals 0. You see, this equation now is a quadratic, you know. It is the same as y squared minus 3y minus 4 equals 0. See that? If you make the y equal this expression in here, it's a quadratic. Just like the variable is x to the 1/3. You can call it y and solve for the y first if you want. So to solve for the y here first, I would factorize y, 1 and 4, minus and plus. Those are the factors. So the y equal -1 or y equals 4. Remember, the y is this thing in here, x to the 1/3. So I'm going to put x to the 1/3 equal -1 or x to the 1/3 equals 4. So now that I have that, guys, how do I get x now? How do I get x? You see this x to the 1/3 same like cube root, you know. This side is same as a cube root of x equal -1. This is same as the cube root of x equals 4. All right, how am I going to get x now? What's the inverse of cube root? Cube. Cube both sides. So I cube both sides. We get rid of the cube root. Cube both sides. So I get, if I cube this side, it becomes x. Write it out. Cube both sides. This side becomes x. This side becomes -1 cubed. Or this side again becomes x. This side becomes 4 cubed. So x equals -1, x is still -1. -1 cube, sorry, is -1. Or this cube is 64. 4 cube is 64. Those are the answers. -1 and 64. -1 and 64. Let me see if there's another this guy's quadratic equation here. If I get one in the classwork. All right, so one right here. So I'm going to do this one, and then I'm going to look at the logs. Do a couple logs. Yeah. Quick revision. You know I'm relax. You know I'm relax. You know I'm enjoying my teaching. This is revision. It's not really teaching. It's the revision. All right, we're doing this one. This is this guy's equation, right? Let's write it down. It is 2 to the x plus 2 squared minus x. So we're going to have to pull this up, right? We're going to have to pull this up right here. Equals 5. Remember, when you subtract powers, it really means that you're dividing. When you subtract powers here, it really means that you're dividing. All right? So it comes back unchanged, which is 2 to the x plus. This now is the same as 2 squared. This minus means that you're dividing by 2 to the x. So it's 2 squared over 2 to the x. And this is now equal to 5. But understand that? How to go to that? You see it? You don't see it? Because this comes from the division law. You have to know, say, a number to the x minus y is the same as a to the x divided by a to the y. A to the x divided by a to the y. That's the second law. So we tend to learn the law from left to right like this. Like a to the y divided by a to the x equals, you subtract the powers, right? A to the y minus x, you know that, right? When you divide indices, you subtract the powers. If you know, so you can go that way too. If the powers are being subtracted, it means that you're dividing. See? That's what I did here. So these powers are being subtracted. So it means that it is this one divided by this raised to that. So the subtract means when subtract is in the power. So I pull it up, I pull this up and I write this. This 2 squared divided by, the minus means divide, by 2 to the x, which is what we have here. So, see it? All right, so we're solving this now. So what I have to do now is multiply 2 by this 2 to the x. Let me write it out. Multiply by 2 to the x. And multiply by 2 to the x, this becomes 2 to the x squared. 2 to the x squared, sorry. Plus, this just becomes 4, right? And this 2 to the x is cancelled. This 2 squared is 4. Equal, multiply this by 2 to the x, it becomes 5 times 2 to the x. I'm going to transpose this over here so now and get 2 to the x squared minus 5 times 2 to the x plus 4 equals 0. See this now, it is the same as y squared. If the 2 to the x is y, same as y squared minus 5 times, it's like y again, plus 4 equals 0. So I can solve it for y now. So you can factorize this. It's y, 1 and 4 minus minus. That's what this factorizes into. So you're getting y equals 1 or y equals 4. Remember, the y is 2 to the x right here. So it means that 2 to the x is equal to 1 or 2 to the x is equal to 4. Now, if 2 to the x is equal to 1, what is x? 0. Any number raised to the power 0 is 1. So x equals 0 right here. So if 2 to the x equals 4, what is x? Huh? If 2 to the x equals 4, what is x? 2. 2 squared is 4. Those are the answers for that one. All right. So you're getting a question on the classwork similar to this one. Very similar to this one. I'm going to have a sugar question on the classwork as well. Let's talk about logs now. Quick recap of what logs are. And look here, you can't the logs question unless you know the laws of logs. Tell you that up front. If you don't know the laws of logs, you can't move from a logs question. Logs very, very easy. We have to know the laws first. You have to know the laws from left to right and from right to left. Good? Now, logs and indices have a nice relationship. And I'm going to start with that. So, the log, this is something that is good to remember. The log of a number to a base is actually equal to a power. The log of a number is really equal to a power. The log of a number is really equal to a power. This is the number, this is the base, this is the power. It means that this number, n, is equal to this base raised to that power. So these two expressions can go backwards and forward on each other. This implies that, and this implies that. That's the relationship between logs and indices. The log of a number to a base is equal to a power. Means that that number is equal to this base raised to that power. See there, the base raised to the power. That's the relationship between logs and indices. So if you have indices, you can convert it to logs using this. If you have logs, you can convert it to indices using that. You just need to identify the number, the base, and the power. So in the log form, the number is here, the base is here, the power is the answer. In the indices form, the number is what is equal to the base raised to the power. So the log of a number is equal to a power. The log of a number is equal to a power. The log of a number is equal to a power. What power? The power to which you have to raise the base for it to be equal to the number. That's what it is. Example with some numbers now. So the log to base 10 of 100 is equal to 2. Why is that? Because 100 is equal to 10 squared. See, the number 100 is equal to the base 10 squared. The log of this number is the power to which you have to raise this base to get back the number. Right? Using other values. The log of 8 to base 2 is actually equal to 3. How I know that? Because I know say 8 is equal to this base cubed, which is true. So the log of 8 to base 2 is equal to 3. Because you have to raise 2 to the power 3 to get back the number 8. All right? That's the relationship between logs and indices to begin with. It's a lot, but we actually do a whole class with this already. So coming for the first time, it's a lot. All right? Then we can talk about the laws of logs now. And I'm telling you, if you're gonna get logs question right, you have to know the laws. All right. You have to know the laws from left to right and from right to left. So the sum of two logs become the log of the product when the base is the same, like this now. The log of A plus the log of B. Let me use not A and B. Let me use X and Y. Log of X plus the log of Y raised to the same base becomes equal to the log of the product. The log of X times Y to the same base. That's the first law. So when you add logs, it becomes the log of the product once the base is the same. All the laws of logs, no, not all of them. For add maths, you only have same base laws in add maths. In pure maths, there's a change of base law that you must know for pure maths. But see, say add maths, only single base laws you have to. The first 3 laws are single base laws. Now you have to know this law from left to right. You have to know it from right to left. Both ways. Give me some examples now with some values. So for example, if they give me, let me write an example with some values. So if I have the log to base 3 of 2 plus the log to base 3 of, let me use 5. Let me use X. This becomes equal to the log to base 3 of 2x. Multiply them. See that? But you might have a question where you have the log to base 3 of a log to base 3 of, I want to use something else, of 5p, and I have a need to split that up. I must know that this is the same as the log to base 3 of 5 plus the log to base 3 of p. So this law up here, you have to know that it can go both ways. You have to know the law from this side to that side and from this side to that side. You have to know it both ways. That's the first law, the addition law. Then you have the subtraction one now, which is very similar, just that you're dividing. Subtraction one. So the log, what did I use? X and Y. All right. The log of X minus log of Y becomes the quotient, becomes the log of X over Y. But the base is the same. Base is the same. Base is the same. So when you subtract logs, it becomes the log of the quotient as the second log that you must know. So this is the first one up here that you must know. It's now the second one that you must know. You have to know it from left to right and from right to left. Let's use some numbers now as an example in red. What did I do up here? Purple. Example in purple. If I have the log to base 3 of 2 or of X minus the log to base 3 of 2, I can write that instead of the log to base 3 of X over 2. I divide this by that, X over 2. But you might have a case where you have a quotient and you need to pull it up. Like for example, you might have, give a nice example now. You might have the log to base 3 of X plus 1 over X plus 5. You might have a need to pull this up. It becomes the log to base 3 of the X plus 1 minus the log to base 3 of the X plus 5. So I pull this up. You have to know the laws, guys. But there's some questions I show it in. I know that a lot of you come for the first time, can't teach over from scratch. All right, that's the second law that you all must know. So the first one I call it the addition law. When you add logs, it becomes the log of the product. The second one I call it the subtraction law. When you subtract logs, it becomes the log of the quotient, the divide. The third one I call it the power law. The power law. The third one I'm going to look at now. The power law. So like you have the log of a number raised to a power, to a base. The law says that this power can come to the front as a multiple. So this is the same as x times log to base b of a. That's what it is. This power can come to the front. All right, so you get the log of a with the same base b, but the power comes to the front. Call it the power law. The power law. Those are the three basic laws that advanced students must know and use. Pure math students, there's more for you. Change of base law. But maybe we'll come some example with this one with numbers. So for example, I might have the log to base 3 of x squared. I can take this square and bring it to the front and write this instead as 2 times the log of x to base 3. I take the 2 and I bring it to the front. Can I have another example where they give me, 5 log to base 4 of y. And I need to get this power, this number from in front. I will bring it up here. And so it becomes log to base 4 of y to the 5th power. So I go going from this one to that one. All right. Now look here. I can make you know the laws in one day by just being exposed to it for the first time. You have to go and study them and use them. You have to go and study them and learn the laws from left to right and from right to left. The best way to know the laws really is to practice. Yeah, the 5 can come up here, so take the 5 and bring it up as a power. Or if the 5, if you have a power, you can bring it to the front. Right? You have to be able to go both ways. have to learn to go both ways. You get me? So those three are for add maths. Then there are some general must know things about logs as well. The log of a number to its own base is equal to 1. So the log of a number b to the same base b is equal to 1. Why is that? Because b is equal to b to the 1. Remember, this is the number b. This is the base raised to the power 1. So log of a number is 1 means a number and the base is the same. Log of a number to its own base is equal to 1. Next thing, you can't find the log of 0. Log of 0 does not exist. And you can't find the log of a negative number. Right? So in this law right here, in this thing that I gave you earlier, let me just write it right here. So the log of a number to a base is equal to a power. So this number, n, has to be greater than 0. Can't be 0 and can't be negative. The n has to be greater than 0. Because the assumption is that the base is a positive number. It's the assumption the base is a positive number. So the n has to be greater than 0. The n has to be greater than 0. So if you do a question with the logs, and it turns out that the answer that you get will cause you to find the log of a negative number, you can't accept that answer. Because the n has to be a positive number. It can't be 0. Right? It can be 0.1. It can be 0.00001. The next thing is that the log of a fraction is negative. You can try it on your calculator. Like, for example, the log to base 10 of 0.5. You're going to get a negative answer for this. Somebody try it. You're going to get a negative answer. Negative, equal and negative value. The log of a fraction value is negative. Log of a value less than 1 is negative. You can try. Log of any number less than 1. A fraction value is negative. Remember, it has to be greater than 0. It's negative. It's very useful for add math students. We did question the other day with it. What's the change of base law for pure maths? How many people in here doing pure maths? 1, 2. 1 and 2. You have to know the change of base law. The change of base law is this. Easy. The log, the log of a number to a base. You can introduce a new base. Easy, easy. You take the log of this over the log of this base. And you introduce any new base. Let's call the new base m. That's a change of base law. Any new base. So log of this over the log of this to any new base. Get me? That's a change of base law. You want to change the base. Let me use some numbers and I'll show you. So for example, if I have the log of 5 to base 3, I can change the base, for example, to say 7. And write the log of 5 over the log of 3. And I can put any base I want. I can put base 7. I can put base 10. I can put base 50. I can put base just B. Any new base. Any new base. Then we have the reciprocal one now, which is this. You can actually flip the base and put 1 over. So for example, the log of a number to a base is equal to 1 over, and you switch around these two. The log of B to base n. It's really an extension of this law up here, so that's what it is. Now what I've done is make the base be n, and this becomes 1 up here, so. All right. Some questions now. So go to my class, I'm a tile and not a tile. So go. Not a tile. Everything is being recorded. So you can go back and watch the video, 10-minute segments if you don't want. Everything is being recorded. All right. Remember, this is something that we did already in a class. It's a revision. It's actually a revision right now. I'm going to give you a classwork to do after. I'm going to do a couple questions. I'm going to do a couple logs questions now and show how we can apply some of these things. All right, let me go back for the other sheet. There's another sheet that has some logs on it. Let me go back for it. And do a couple questions on it. All right, let's look at this first one here. Simple. Solve that equation. All right, so I'm going to tell you something now. That is very important. All right, so you have a general approach that you want to use when you're solving logs questions. Remember, applying the rules, the laws of logs, but there's an approach that you want to use each time solving a logs question. You have an approach. So this is it, guys. Pay attention. Pay attention. When you're solving a logs equation question, right? You want to reduce that logs equation to one of two forms. You want to reduce to solve logs, to solve or simplify logs expressions. Reduce it to one of two things. One, log of n equals log of m to the same base. So you reduce it down to log of something on one side equal log of something on the next side. This would then mean that the n equals m, and then you solve this. Simple as that. That's the first way. So you want to take the left side, bring it out to one log expression. Take the right side, simplify to one log expression. Two sides have the same base. So it means that the two values them equal. And then when you get that, you solve that. That's the first approach. The second approach is the one that has to do with the law, with the what logs is, the log relation with the logs and indices. Second approach. You reduce to, instead of reducing to this, you reduce to this. The log of a number to a base on one side equal a value on the other side, which that value is a power. And when you get that, this then would imply that this number n is equal to this base raised to that power. And then you solve this. Can't go wrong. So you start doing a logs equation, a logs question, and you want to simplify it or solve. Your aim is to get it, your logs equation simplified down to this. So you can get this to solve, or get it simplified down to this. So you can get this to solve. One of those two you're aiming to do. Simple as that. So I'm going to do it with this one. No. All right. All right, let's go. So I have this logs equation to solve. Let's look at it. It is the log of x minus 4 plus 2 times the log of 3. Oh, by the way, when we say LG like that with no number, it means logs to base, it means logs to base 10, right? It means log to base 10. Or if you say LOG and they don't show no base. Once they don't show a base, it's base 10. Pure math students, you will see ln. ln. This is log to base E, and it's on your calculator. All right, so advanced not going to get ln. Pure math students will get ln. All right, So this now is equal to 1 plus log of x over 2. Now look here, guys. Don't do this. Don't say I'm going to expand the log over them to something here. Like you write this as the log of x minus the log of 4. This is not a multiplier. It's not a multiplier. It's a statement. The log of something. You get me? It's not a multiplier. It's not a factor. It's not a multiplier. You understand? So don't do that, please. You're going to apply the laws of logs. See a plus right here, so it's about 2 in it. The laws of logs, if you have no number in front of this, so I need to get rid of this 2. What do I do with it? Put it up here, so. Get me? Now, the first question is, what approach are we using to solve this? Are we bringing it down to this one? Or do you want to bring it to this one? Either one can work. Based on this equation, which one would you aim to do? To go at? You want to bring it down to log of a number equal log of another number? Or you want to bring it down to log of a number equal a power? Which one? This one or this one? Which one? Since we have log on the side, I'm going to work with that one here. Bring it down to that. But I will need to convert this one into logs as well. All right? So I'm using the first one. I'm trying to get the first one. So I want the left side to become 1 log expression and the right side to become 1 log expression. All right, let's go. So I need to move this 2 first. Sorry. The power law said the 2 can go up there, so you have to just know the laws, guys. So this comes back unchanged. The log of x minus 4 plus, I'm going to put the 2 up here, so I write it as the log of 3 squared. I'm writing it there. I could just put the 9 there, but I'm going to write 3 squared for now. Now see this 1, to convert it to logs, I just multiply by the log to the same base. I'm going to show you something right now. If you have a number, I'm going to show you something right now. If you have a value like, for example, 3, so I have plus 3. So I have an equation log of something x plus, let me give an example. Let's say I have an expression log to base 3 of x plus 4. I'm going to convert this into 1 log expression. I need this 4 to become a log. All I have to do is multiply it by log to base 3 of 3. If I want this number to become a log to base of 3, but let's multiply it by log of 3 to base 3. Why is that? Remember, this is equal to 1, you know. Log of a number to its own base is equal to 1, right? And when we multiply by log of a number to its own base, using the power law, I can take this 4 and bring it up here. So this then would become, put it back in red, equal to log to base 3 of x plus log to base 3 of 3 to the 4th power. When this comes up here on the power, I get 3 to the 4th power. And 3 to the 4th power is 81. So this then will become log to base 3 of x plus log to base 3 of 81. Then this plus now means that I can multiply the values. So this will work out to be log to base 3 of x times 81 is 81x. See that? So that's how you convert a value to logs. Just multiply by the log of whatever the base is to its own base. And then move the number as the power up. Simple as that. All right? So back to this question up here now. I want this one to become a log to base 10. So I'm going to multiply by a log to base 10 of 10. But 1 is the same as log to base 10 of 10 anyway. Remember, a log of a number to its own base is equal to 1. All right? So anyway, you want to look at it, this becomes log of 10. to base 10 become the log of 10. That's what this one becomes, the log of 10. Plus the log of x over 5. X over 2, sorry. So far, so good? What do you understand? Huh? Which part do you understand? Huh? You don't know where you don't understand? All right. So, all right, ask me now, they give me this to solve. And I said, when you're solving logs, your aim is to bring your logs down to one of two things. Either bring it down to look like this, or you bring it to look like this. Because this equation that they gave me had logs on both sides. I decided to use the first one. I want to bring it down to one log expression on the left side and one log expression on the right side. You absolutely cannot do logs unless you know the laws. Where you at the last class? One over a week ago. I said, no, go and study the laws them. Did you go and study the laws? So you're right back where you started. All who never go and study the laws, you're right back where you started. You can't move in a logs unless you learn the laws first. You'll be lost. You'll be staying in space. You have to learn the laws. You want to do this topic? It's a very, very easy topic, you know. But you have to learn the laws. You doing advanced, you only have 3 of them to learn. Just 3 laws. I had over 9 days to learn 3 laws. I don't learn them. Because the last class was last week, Tuesday. I went on a week break. No, so? No, Friday. Friday. The last class was a Friday. I never keep class on Tuesday. Never keep class on Friday. Never keep class on Tuesday. So 3 classes were missed out. Because I was away. And all of that time, you know, take time to learn the laws of logs. So you come back one of the logs question now. And I said it in the class. You will not be able to do logs question unless you learn the laws first. And it's only 3 of them you have to learn for add maths. And you come back here and tell me you don't know the law them. So how you going to do the question then? So it's almost like we're right back at 2 weeks ago. Because you have not allowed yourself to advance. If you learn the laws, everything gets easy, you know. If you learn the laws, everything gets easy. And we did so many questions. Did I send a recording to the group for those questions? But we did a lot of questions. Possible questions. Did I send a recording to the group? Huh? I did, don't it? Yeah, so now no excuse. With a pure maths question and with the add maths question, a lot of logs question. Pure maths and add maths. And come back here looking at space. Not serious. You're not serious. Start out good. Let me tell you something. It's not a C-second boss. There are new things that you have to learn. I mean, I tell you the new things that you have to learn. It's easy, you know. But to make it easy, there are certain things that you have to learn. And I said to you, you cannot do logs unless you learn the laws first. If you know the laws, then these simplification things become easy. As soon as you say this, you're supposed to know the law. I say this can cooperate as a power. As soon as you say this plus, you're supposed to know the law. So when you add in logs, it becomes the log of the product. Simple. Right? I will do a question, we deal with a 1 already. We do a question with that same 1 already. We did one the other day. So if you do watch back the video, I read the question that I always say. What I always say. Question that we do in the class, you go and redo those same questions before you do any new question. So if you have just gone and redo the question that we did in the class, the last one, then this a breeze. It's the people who knew me go through all this final. People who knew me not do it for no. Because I'm supposed to clear this already. So all this time I go through this, it's just for the people who knew. But come like I want to benefit more than the people who knew. Anyway, I'm not going to get this in. But guys, you have to take time to learn the laws. If you don't know the laws, you'll be stuck. in quicksand with this topic. But if you learn laws, smooth sailing, I tell you. So it's up to you. Take the time. It's 3 laws, 3, bad maths, 3, dege laws. The addition one, subtraction one, and the power one. 3 dege laws. You get me? So good. So we are here now. So now we have this plus. Means that I can multiply these two values under one log. First law. So this side becomes the log. This is 9 times this. Now, baby, you know, equals. Same thing on this side. Plus becomes the log of 10 times that. From the log of 5x. Because 10 times this cancels into this 5 times. Cancels 5 times. 2 cancels into 10 5 times. Now, me have the log of this equal the log of this. It means that something equal to something. Common sense that. If the log of one expression equal the log of another expression, then the two expressions they must equal. That's not maths, that's a common sense. If the log of something equal the log of something else, then the two something they must equal. So it therefore means that the 9 into x minus 4 is equal to 5x. And that's why you reduce. That's why you're solving now. So this is like the m and it's like the n. I'm going to say we must solve m equals n and solve. So we are solving that. That's what I said. This is 9x minus 36, right? Equals 5x. Transpose that, we get 4x. Transpose the 36, we get 36. So x equals 9. Simple as that. See there? It's not complicated. It's quite simple actually. But you have to learn the laws, guys. You have to learn the laws. You have to learn the laws. I feel like we need another day. I feel like we need another day on this. No. I feel like we need another day, but we are waste time. Now we'll give back some Sundays if that's be the case. We'll give back some Sundays. We'll make it up back with some Sundays. If we not bother do the thing to learn us practice some questions and we not chance rather than go to the classroom. I really wanted to move from this topic this week and start a different topic Tuesday. That's the plan. But when you look so comfortable, I like when you look. I like when you look. I like when you look. And you see, especially period maths, you see logs and armor, logs on every paper. Same thing with advanced logs come a lot. You don't learn the laws and you can't do the questions, guys. You don't learn the laws, you can't do the questions. All right. Leave that one a little bit. Let's find another straightforward one to solve. Let's find another straightforward one to solve. All right, let's do this one. I'll come back to this one afterwards, right? Just want to find some straightforward ones. Let's look at this. Solve this equation. So this one now, they have a number over here. So naturally, I'm going to use for this one, I'm going to use the second thing that I showed you. See here, I'm going to use this now to solve this one, this format. I bring the side that to 1 log expression equal to 2. Right? This for this one. For this question, I'm going to use this thing over here. So this. Bring it to that. I have a number up on the right side, like my P over here. So. Right? So I give you the framework to solve these questions. All right? So let's look at this one now. And then we'll go to the third question. It's the indices. I want to introduce something again. I do some work today and I could have deal. So I have this thing, right? Again, if you don't say the base, it's base 10. So I have log of x plus the log of 5, well, this is just 5x plus 5. Let's write as 5x plus 5. This is just 5x plus 5 equals 2. There's no base shown there, so no, it's base 10. Base 10. When you add logs, it becomes the log of the product of these two things. From the log of the product. So this side becomes the log of x times this. Let's write it out for you. X times 5x plus 5. And it is equal to 2. I'm going to put this as one expression. The log of 5x squared plus 5x is equal to 2. This base is 10. Let me show it for you. 10. So this is my n. This is my b. And this is my p over here. So this number is equal to this base raised to that power. So I brought it down to the formula that we wanted. Simple now. Base is 10 when it is not shown. So this number, which is the 5x squared plus 5x, is equal to this base of 10 raised to this power of 2. Remember, the log of a number is equal to a power. The number is equal to the base raised to the power. That is it. This is just 100 now. So it means that 5x squared plus 5x is equal to 100. You see, I'm divided 2 by 5. So 5 divided 2 by 5, I get x squared plus x is equal to, this divided by 5 is how much? 20. Transpose the 20 and subtract. X squared plus x minus 20 is equal to 0. You see, I'm factorized. X and 4 and 5 plus and minus are the factors. So you're getting x equals 4, x equals negative 5. Don't run away just yet, especially when you get negative values. You have to ensure that this value, if you put them in the original question, will be such that you're not trying to find the log of a negative number or the log of 0. So I put a negative 5 in this one. It can't work. Look. If I put x equal negative 5 in this one, it can't work. Because you can't find the log of negative 5. So x can't be negative 5. But understand that? So we cannot accept negative 5 as an answer. So this answer is not valid. Right? It will cause us to be putting in a value that is not valid. So this one is not a valid answer. So this is the only answer right here. That is good. But you can't find the log of a negative number. So x can't equal negative 5. So you have to invalidate that answer. All right. All right, let's do the second one. This one right here. And listen to me carefully now. Let's do that one. But okay with this one? All right. No good? Okay. Let's do the second one now. So one question for doing it. I think I may have all of them. Now what is now? They give me this to solve. 3 to the y plus 1. 3 to the y plus 1 equals 0.45. Tell it from now. Tell it from now. When the thing that you're trying to find is in the power, you must take log to get it out of the power. I remember, you know, when you take the log of a number to a power, the power can come to the front. Remember that, right? So to get this y from out of the power, we can take logs. You can't take logs. When the number that you're trying to find is in the power, you can take logs to get it out of the power. So we take log of both sides of this. So we'll log the left side. Let me write it down. We want to log the two sides. So you're going to get the log of 3 to the y plus 1 equal the log of 0.45. 0.45. That's it, right? Then now this power can come to the front using that law of logs, the third law, the power law. So you move it to the front, but remember you're moving the entire thing, you know. So it becomes y plus 3, not y plus 3, y plus 1 times the log of 3 remains, because the power is now at the front right there. Log of 3 remains equals the log of 0.45. So you're solving this for y now, easy. Take this log of 3, divide it under here, so, and then subtract the 1. See it here? So y equals the log of 0.45 divided by the log of 3 minus 1. Understand that? Understand how I got that? Divide by the log of 3 first. And then this 1 right here, I subtract it over there. So that is the answer. Put that in the calculator and get the answer. That is the answer right there. All right. That is that. Let's see what other questions I have here. All right, come guys, you tackle this one for me now. Because like, let me can't bother going to work today now. I'm not ready for it. Another day. Come, tackle the question for me, let me see. This one. This one right here, so easy question. This. It's a given that log to base 3 of x minus 1 is equal to 2. Evaluate the log of x. Come on, this one, let me see. The more the log of x. To find the log of x, you might multiple ways to do it. Remember, this mean log to base 10, right? LG mean log to base 10. So given this thing, find the log of x. Maybe we can just find x first from this equation. Come now, 2 minutes to do it. 2 minutes. I want more than 2 minutes. Come on. 2 minutes to do that one. Try it. Remember this. The log of a number to a base is equal to a power. So in this expression right here, so let me set up for you. This thing in here so becomes a number. This is your base. And this is your power. When you have this set up, the number is equal to the base raised to the power. This goes to that. And this is a number, this is a base, this is a power over here. Do that one for me, quick. 2 minutes. Don't need more than 2 minutes. Come on, youngster, take out the pen and start working. The one in purple you're doing, come on. That don't need a minute to do. You finish? You done? Get it? All right, this second one in the meantime then. Finish the first one, the second one. Go on. And the third one. Yeah, just do the whole question. So far you can read. First one, second one, third one. Right here. First, second, and third. What other question here, sir? A, B, and C. Alexander, you doing the question?
Yes, sir.
Yes. All right. How did man board now? I know that. How did man board? 1 minute, 1 minute. How did man board? Done? Try that one. Done? You done? What's up now, man? Huh? You done? Second one. Very good. All right, final one. Gonna start. Finish. Am I done now? 7:15. Huh? Done? Finish, mom? Try another nothing. All right. Alexander, you finished?
Yes, sir.
All right. Back it around. Impossible. All right, ready? Ready, let's do this. All right, the first one, A. They give us log to base 3 of x minus 1 equals 2. This is a number which is equal to this base raised to that power. So you can write that. You can say that implies that this number x minus 1 is equal to this base of 3 raised to the power 2. This 3 squared is 9. 3 over the 1 means that x is equal to 10. Then we want the log of 10 now. That's what this one to know, log of x, which is the log of 10. So we can say, therefore, the log of x really is the log of 10, which is equal to 1. All right? Our next one now. All right. Next one. This one now. Let's go. So this one has logs on both sides. So I think this to solve this one, we want to bring it to a case of the log of a number equal log of another number. So that the two number them equal, n equals m. I think that's the best approach for this one. All right? So let me write it out for you. The log of 3x plus 2 plus 6 times the log of 2 equals, some more space. Equals 2 plus the log of 2x plus 1. All right? This 6, I need to move it. And so I need to move this 6 up here. So left side becomes the log of 3x plus 2 plus the log of 2 to the 6th power equals this 2. I need to convert it to logs. So I multiply it by the log of 10. The log of 10 is 1. So I'm going to get 2 times the log of 10. Multiply this by the log of 10. Put this in red. Right? I multiply by log of 10 because LG mean log to base 10. And I'm writing this back. This don't change it. Plus the log of 2x plus 1. Well, this 2, we're going to come up here now. All right? And then this is what? 2 to the 6th power is how much? So this is going to become the log of 3x plus 2. I'm going step by step for you, right? Plus the log of 64 equals this 2 come up here, so I get the log of 10 squared. Normally, I just write 100 in them. I'm going step by step for you. Plus back this thing now. The log of 2x plus 1. Then I can put these two together, add them. Because remember, when you add logs, you're going to multiply the values, right? So this side becomes the log of 64 times 3x plus 2 equals this side, this is 100, right? This is 100. So it becomes the log of 100 times this. 100 times 2x plus 1. Good? So since log of something equal log of something else, means then that these two things equal. It means that this thing equals this thing. Yeah, log of something equal log of something. The two something must equal. Common sense that. So it means then that the 64 into 3x plus 2. Normally I would write out all these steps in, but I was doing it for the first time, this time. Equals 100 into 2x plus 1. And I expand and solve. What is 3 times 64? Huh? Although this time, this can divide by 4 and this can divide by 4. Can divide this by 4 and divide this by 4 as well, don't it? We divide this by 4, I get 16, don't it? Divide it by 4, I get 25, don't it? Okay, expand now. 16 times 3 is what? 48. 16 times 2 is what? 32. 25 times 2x is what? 50x, don't it? 50x. And then 25 times 1 is 25. I know we're solving for x. Take this 48x and subtract over here. So from the 50, I get 2x over there, right? Take this 25 and subtract from the 32 over here, I get 7, not it? Divide by the 2, I get x equals 7 over 2 or 3.5. So x equals 3.5. But I to that? Anybody got it? You got it? You got it? Good. All right, let's do the last one now, the third one. All right, so this one is what we call a disguised quadratic equation. There's a quadratic equation hidden in there. All right, but you have to pluck out the square term and so on. Square term is in this one. So let's go. So we have 3 to the 2x minus 3 to the x minus 6 equals 0. So this 3 to the 2x, by that third law of indices, you can split the 2x into 3 to the x r squared, right? This becomes 3 to the x r squared. But I understand that. Yes, sir. Minus 3 to the x minus 6 equals 0. Now this now is really the same as y squared minus y minus 6 equals 0, don't it? Now I don't really have to do this, you know. I can just treat it as a quadratic. My variable is 3 to the x. I don't really have to do the y business, you know. To me, a waste of time, really. But I just do it for you to see, don't it? Eh? So it's like a quadratic in 3 to the x. Let's do it this time. I'm not going to learn it unless I do it. So I'm going to treat this as treat this as if it was x. And treat that as if it was x. So it's really like x squared minus x minus 6 equals 0. But it's not x, it's 3 to the x. So I'm factorizing it right where it is. Factor of this is 3 to the x, 3 to the x. Factor of this where the difference is 1 is 2 and 3. Signs are different, give the greater product the minus sign. The greater product is the far product. Make it negative. Make that one positive. But I go to that. If you work it to the y and so on, same thing I get it. So this factor gives me 3 to the x equals negative 2. This factor gives me 3 to the x equals 3. Now this one is not valid. Why is it not valid? Because a positive number raised to a power can never ever be negative. Right? A positive number raised to a power can't be negative. Additionally, let's say you didn't know that. I tried to get the x from out of the power by taking logs. They take the log of this side, I take the log of this side. But remember, we can't find the log of a negative number. See that? So anyway, look at it. This one is not valid. The first one is not valid. So we can just put that. We can remember, guys, a positive number raised to a power cannot turn negative, regardless of the power. And we're talking about real numbers here. A positive number raised to a power can't turn negative. Regardless of, there's no power that can make it negative. You get me? So this one is not valid. Then if 3 to the x equals 3, the x must equal 1, right? This is the answer. But good? All right then. Anybody you got that one? Anybody get this one? Anybody get that one all right? Is it right? All right, good. All right, more maths. Let's go again. Let's see what this is here. All right. Do this one for me. Solve those two equations. This one is a logs. This one is a disguised quadratic equation again. This one. Do those two for me. Come on, 5 minutes. Maybe I need to bring up the clock. So we have to do the classwork on Monday. Come, 5 minutes. We're gonna have to do the classwork on Monday. All right. I'm gonna practice. We can practice some questions tonight. Get comfortable with this thing. Not Monday, on Tuesday. Who could come Sunday afternoon? Hmm? Can do it Sunday, do the classwork Sunday instead? Hmm? Online? All right. Finish? All right, my turn. All right, the first question is 2 log x of x equals 1 plus the log of 4x minus 15, 2 to solve, right? All right. I'm going to take this 2 and move it up here. I'm going to convert this into logs. It's going to become log of 10, right? So I'm going to get the log of x squared equals the log of 10 plus the log of 4x minus 15 over 2. Because of this plus, I can form the log of this product, right? So it's become the log of x squared equals the log. Now, when we do 10 times this, it cancels with this 2 5 times, right? So it becomes the log of 5 times 4x minus 50. But I can agree with that? But I agree with that? I'm multiplying this times this. And I get this. But I go to that? Yeah? So it means that this x squared is equal to this. Huh? All I've done is multiply this times this. And that is 1 log. The plus means that I can take the log of 10 times this. And 10 times that is this. See it? Then it means then that x squared, this thing equals this thing now. It's equal to, if we expand this, I get 5 times the 4 is 20x. And 5 times the 15 is what? 75? That's a quadratic. Transpose over everything now. X squared minus 20x plus 75 equals 0. Factors of 75 that add to 20. Factors of 25 that add to 20. 15 and 5. Good. X, 5 and 15. Signs are the same. They are both negative. Minus, minus equals 0. X equals 5. X equals 15. Let's test and make sure that both will work. So both will work. Yeah, man, both of them will work. No, will the 5 work? Yeah, 4 times 5 is 20. Yeah, so both of them will work. So those are the answers right there. The second one is that this guy's equation, this guy's quadratic equation. Let's look at it. So they give us 4 to the y minus 7 times 2 to the y equals 8. This 4 is same as 2 squared, right? So we can write as 2 squared, all right, 2 to the x, to the y minus 7 times 2 to the y equals 8. Then this now can switch these around and write it as 2 to the y squared minus 7 times 2 to the y. Okay, over the 8 again, minus 8 equals 0. That's a quadratic now. It is the same as x squared minus 7x minus 8 equals 0. Good? Same as that. So we're going to factorize it. Factorize this and work with x to be x and x. This can factorize. 2 and 4 can give me 6. Oh, 8 and 1 minus give me 7. Yeah, 8 and 1. 1 and 8 minus and plus equals 0. So x equals negative 1, x equals 8. But x is really 2 to the y. So it means then that 2 to the y is equal to negative 1, or 2 to the y is equal to 8. This one not valid. For the same reason that a positive number raised to a power cannot be negative. And this one, the y is 3, because we all know that 2 cubed is 8, right? So the y is equal to 3. All right, that's that. More maths equals better maths. Let's do another one. All right. All right, come now. Tackle this simultaneous equation for me. See, evaluate P and Q. Teacher, simultaneous equations. All you have to do to solve the simultaneous equation is eliminate the logs out of this one and eliminate the logs out of that one. That's all you have to do. Get the logs out of them. Huh? Come on, man. Get the logs out of them. That's all you have to do. Get the logs out of them. And then when you get the logs out of them, what you have left, you solve. This one is easy. You can, in fact, this first equation only have one unknown, you know, the P alone. So you can get the P from the first equation straight. And after I get the P, I put it here. In fact, you'll be able to find what the log of P is. And then use that same value here. So that question is really very easy. Easier than I thought. Come. You don't need no more than 3 minutes for this one. Don't need no more than 3 minutes. Hey, touch a young telephone. I'm there. You're right, no, man. Huh? No, you're solving for P and Q. But this one is basically, this one only has one unknown, you know. So this one can be solved for P. Straight out of this equation. You can solve for P. After you know P, you can solve for Q from the second equation. It's a very easy question. Okay, now you all have this document, right? You don't have it. So who don't have it? Let me know. I'm sending it to you on WhatsApp for the time being. Let me get the print it on. But since we do all these questions, I need to go and redo them. All right. Now, one more minute. Giving you one more minute. No, man, I'm going to do it on the board. I'm going to do it. I'm soon do it. I'm giving them one more minute. I'm not going to do it. You finished? You, yeah. You done? I want to easy. I want too easy. You finished? Hey, can you see it now? My minute done quick though. All right, come, let's go. Ready? Pay attention. The first equation has one unknown in it. Any equation with one unknown can be solved. The first equation is just the log to the base 2 of P minus the log to the base 2 of 32 equal -3. But because this one is numerical, you really want to be generating this thing from your expression. Log to the base 2 of 2. I know that equal 1. Log of 2 to the base 2. So what I'm going to do, I'm going to write this 32 as 2 to the which power? 2 to the 5th power, right? So it becomes log to base 2 of P minus log to base 2 of 2 to the 5th power equal -3. This 5 comes to the front. So it becomes log to base 2 of P minus 5 times log to base 2 of 2 equals -3. This log to base 2 of 2 is 1. We'll put it in bracket and put 1 on it. So this whole thing is just 5, -5. So -5 over there become a +5. And so log to base 2 of P becomes equal to 2. But as I'm going to get the 2, because this is negative 5. Negative 5 over on that side, become a positive 5. 5 minus 3 is 2. And then what happens is that this P is equal to 2 raised to the power 2. So P is equal to 2 to the power 2, which is 4. P equals 4. Watch this now. Log of 2 to base, log of P to base 2 is 2. So instead of log of 2 to base 2, so log of P to base 2, I can replace it with 2. Right? In the second equation. So the second equation is log to base 2 of Q minus log to base 2 of P is equal to negative 3. But this thing is equal to 2 from right here, so see there? This value, I'm going to use it right here. Right here. 2. So I now have log to base 2 of Q minus 2 equals negative 3. This goes over and become a positive 2. So I get log to base 2 of Q equals negative 1. Then this Q is equal to 2 raised to the negative 1. So Q is equal to 2 raised to the negative 1. Negative 4 means reciprocal. So the Q equals half. Q equals half. Very easy. Could work this out another way, you know, this one. This one. Let's work it out another way. When I use the second log, and say this minus means divide. So this whole expression here will become log to base 2 of P over 32 equal negative 3. So that, and this number we equal to this base raised to that power. So then the P over 32 be equal to 2 to the minus 3. This minus means reciprocal. So the P over 32 would simply be 1 over 2 cubed, which is 8. Then the P now be equal to take the 32 and multiply it up here. So we will get 32 over 8. 32 over 8 is how much? CM4 that we got up here. So it is of P equals 4. But I prefer doing it this way up here because I want to see what the log of P was equal to. So I could use it right here. Yeah, man. That's why I prefer to do that first way. All right, more mass equal better mass. Let's go. All right, this one. You got to go. I'm not finished as yet. Huh? All right, hold on before you go. So I need to hold on. To get your name and the number. Yeah, well, the name is your name and your parents' name. So I can do. But we will not get into it. I decide. I think it's good. Right about it. Yeah, man. Everybody write the name. Everybody write the name. All right, yeah. Everybody write the name. You already write your name. You need to already. You need to already write the name. All right, I call it tonight. Yeah, man.
Today I was in them early 1990 question I was not understanding. If I was like 2012, they would have get it.
Everybody write the name on the paper. You're not gonna do write the number as well. I experience number. All right, Alexander. We're in the class now, yeah?
Okay, sir.
Okay, sir.
I end it now.
Yes, sir.
I didn't man paper. What? I am mother number two. So now I'll both enter WhatsApp.
What's up, sir? What's up, sir?
Yeah, man, Atina, what going? You good?
Yes, sir.
So why you never come face to face class?
Sir, me never remember see you today, sir.
Oh, all right. Well, the session recorded still, so I'll share it in the group later. I'll update the group with all the names and share it in the group.
Sir, when I watch my YouTube from it start, sir.
Oh, okay, all right.
You see.
All right, cool. All right, later, here, man, end the session now.
Yes, sir.
All right, Alexander. All right, bye.
Bye.
All right.